Welcome back to Second Career Pilot.
Thanks for having me.
You sent over some really interesting stuff this week, and
Yeah,
I think what we should do is unpack these fundamental principles of how airplanes actually fly.
sure.
Um, and I think this will really help you out.
Yeah,
Kind of getting started on your pilot journey.
absolutely.
So we'll be looking at those core concepts that underpin everything that you're going to learn in flight training.
Yeah, it's really understanding the rules of the road before you
Right.
get behind the wheel. So
Yeah.
you've provided some great resources, and we're going to break those down
Oh,
and
yeah.
focus on those key takeaways.
All right, so let's jump right into it.
Okay.
The foundation of flight really comes down to what are known as the four forces acting on an airplane.
Right.
I'm sure you probably encountered these in your material.
Yeah.
The first one is lift.
Uh-huh.
Now, simply put, what's lift doing for us?
Lift is that upward force that directly opposes the airplane's weight and keeps it aloft.
Right.
It's primarily generated by the wings.
Okay.
And you might have seen some diagrams in your readings that showed this special shape of a wing called an airfoil.
Right, that curved upper surface
Yeah.
and a flatter lower surface.
Exactly.
So if lift is pushing us up,
Mhm.
what's...
Thrust is the force that propels the aircraft forward through the air.
Okay.
In a typical small airplane, this comes from the engine turning a propeller.
Right.
Or in jets, it comes from the exhaust of the engines,
Right.
pushing air backwards.
Okay.
It's all about creating that forward motion.
Okay, so what's the force that's always working against that forward movement?
So that's drag.
Okay.
And drag is the resistance the airplane encounters as it moves through the air.
Uh-huh.
It's a little bit like friction that you feel when you try and push something through water.
Got it.
The air resists the airplane's passage.
Okay, so in a nice, stable level flight,
Yeah,
the kind you'll be aiming for most of the time when you're cruising along,
right.
what's the relationship between these four forces?
In that ideal scenario, they are balanced.
Okay.
Lift is exactly equal to weight,
Uh-huh.
so you maintain your altitude,
Okay.
and thrust is exactly equal to drag.
Right.
So you maintain your speed.
Got it.
It's a state of equilibrium. Right.
But you noted in one of your articles
Yeah.
that balance changes
Yeah,
when we want to climb or descend.
exactly. And
Right.
when your flight path isn't horizontal,
Yeah.
you can think of these forces as having components that are in different directions.
Okay.
So, for example, if you are climbing,
Yeah.
some of the thrust from the engine is actually helping to pull you upwards
Yeah.
as well as forwards.
Interesting.
And conversely, when you're gliding with the engine at idle,
Uh-huh.
it's actually a component of the aircraft's weight
Okay.
that is pulling you along that downward flight path and
Correct.
acting like a forward propelling force.
Interesting.
So the fundamental forces are always there,
Uh-huh.
but their impact on the aircraft's motion
Yeah.
changes depending on the situation.
Okay, well, let's move on to another
Okay.
another really crucial concept that I know came up in your reading,
Yeah.
angle of attack,
Angle of attack.
or AOA as the pilots call it.
Yeah.
In simple terms, what is it?
Yeah. Angle of attack, or AOA,
Yeah.
is the acute angle between the chord line of the wing
Okay.
and the direction of the relative wind.
All right, so now we're throwing out some terms.
Yeah.
What's the chord line?
So if you imagine taking a slice through the wing,
Okay.
the chord line is an imaginary straight line
Okay.
that runs from the very front edge of that wing slice,
Huh.
which is called the leading edge,
Right.
to the very back edge,
Okay.
which is called the trailing edge.
So just a straight line across the wing.
Exactly.
All right, and what about the relative wind?
The relative wind is the direction that the air is flowing
Okay.
over the wing as the airplane moves through it.
Okay.
It's always the exact opposite
All
of
right.
the direction the airplane is traveling.
Okay.
So if you're flying straight ahead, the relative wind is coming straight at you
Right.
from the front.
Okay, so the angle between that imaginary line
Yeah.
on the wing and the oncoming air,
Uh-huh.
that's the angle of attack.
That's the angle of attack.
Why is this so important for a pilot to understand?
The angle of attack is the primary factor
Okay.
that determines how much lift your wing is generating at any given airspeed and wing shape.
Okay.
Generally speaking, if you increase the angle of attack,
Yeah.
you increase the lift.
Okay.
It's also a key factor in understanding when the wing will stall,
Right.
which is something you'll learn a lot about in training.
So if I'm flying at a slower speed,
Uh-huh.
do I need a different angle of attack
Absolutely.
of when I'm flying faster to maintain the same level of lift?
Yes, because at lower airspeeds, the wing isn't cutting through as much air each second.
Right.
So in order to generate enough lift to stay airborne,
Okay.
you need to increase the angle of attack.
Okay.
You're essentially presenting more of the wing surface to the oncoming air to deflect it downwards and create that upward reaction force.
So it's like if you were trying to scoop up more water with a net.
Yeah.
You know, if the water's flowing slowly,
Yeah.
you need to angle the net more.
Exactly. Exactly.
And as my airspeed increases, what happens to the angle of attack needed for level flight?
As you fly faster, the wing becomes more efficient at producing lift because more air is flowing over it.
Okay.
So to maintain that balance where lift equals weight and stay at the same altitude, you need to decrease the angle of attack.
Okay.
The wing is now meeting the air with more force.
Right.
So you don't need to present it at such a steep angle to get the same amount of lift.
Makes sense.
As you gain experience as a pilot, you'll develop a feel for coordinating the angle of attack and the engine power to maintain steady flight at various speeds.
Okay, let's dive a bit deeper into lift itself.
Right.
One of the sources you shared mentioned that lift is proportional to the square of the aircraft's velocity.
That's right.
What's the practical implication of that for somebody learning to fly?
It's a really critical concept to grasp.
Okay.
When we say lift is proportional to the square of the velocity, it means that if you double your airspeed, the lift generated, assuming the angle of attack and other factors stay the same, doesn't just double.
Right.
It increases by a factor of 4.
Wow.
That's a huge difference.
That is huge.
Conversely, if you have your airspeed, your lift reduces to only a quarter of what it was.
Okay.
So this really highlights how sensitive lift is to changes in airspeed, especially during takeoff and landing.
Wow, that really puts into perspective why maintaining the correct airspeed is so emphasized in flight training.
It is.
You also mentioned there's an actual equation for calculating lift.
There is.
Can you break that down for us?
Sure. So the lift equation looks like this.
Okay.
L equals CL times rho times V squared times S.
So what are all those variables there?
L, of course, stands for lift.
Okay.
CL is the coefficient of lift, which is a measure of how effectively the wing generates lift at a given angle of attack and shape.
Got it.
Rho. That's the Greek letter.
Right.
Represents the density of the air. Thinner air at higher altitudes produces less lift.
Okay.
V squared is your velocity squared, which reinforces that point we just made about the importance of airspeed.
Right.
And S is the surface area of the wing.
Okay, so this equation really shows how the shape and angle of the wing, the speed of the air, the air density and the size of the wing all work together to create that upward force.
All those factors play a role.
And as the equation shows, if you increase your speed, V squared goes up, the lift will increase unless you do something else.
Yes, exact.
To stay in level flight, you typically reduce the coefficient of lift by decreasing the angle of attack.
That's right.
Conversely, if your speed decreases, you'll need to increase the CL, usually by increasing the angle of attack to maintain enough lift to support the airplane's weight.
You got it.
Now, I know there's a limit to how much I can increase that angle of attack.
There is.
I've heard about the critical angle of attack. What happens if I exceed that?
This is the maximum angle at which the wing can effectively generate lift.
Okay.
If you increase the angle beyond this point, the smooth flow of air over the top of the wing starts to break away, becomes turbulent. This is called a stall. And it results in a rapid decrease in lift. So it's crucial to be aware of this, especially at low airspeeds, like during takeoff and landing, because you might be operating closer to that critical angle.
Without realizing it.
So as a pilot, how do I actually control the amount of lift the wings are producing?
The primary way you control lift is by adjusting the angle of attack. You do this using the control yoke or the stick in the cockpit. Pushing the yoke forward decreases the angle of attack, which reduces lift. Pulling back on the yoke increases the angle of attack, which up to that critical angle increases lift. So this direct control over the wing's angle to the airflow is fundamental to controlling the aircraft's altitude and overall flight path.
Let's switch gears now and talk about drag. You mentioned earlier there's two main types. What are they and how do they affect us in flight?
So drag, the force that resists movement through the air, is broadly divided into two categories.
Okay.
Parasite drag.
Okay.
And induced drag.
Understanding both is really important for efficient flight.
Parasite drag sounds like something we want to minimize.
It is. It's not helping us stay airborne.
What exactly is it?
Parasite drag is essentially the resistance caused by the airplane moving through the air. It's not directly related to the production of lift.
Okay.
There's three main components to parasite drag.
All right, so let's break those down.
Okay.
What's form drag?
Form drag is the resistance created by the shape of the airplane as it pushes through the air. Think about a flat plate moving through the air versus a streamlined shape.
Okay.
The flat plate has to displace a lot more air abruptly, which creates turbulence and resistance, whereas a streamlined shape allows the air to flow around it more smoothly.
Makes sense.
It reduces drag.
So the sleeker the airplane, the less form drag it'll have.
Exactly. Things like the engine cowling, antennas, and the overall shape of the fuselage all contribute to form drag.
Okay, what about interference drag?
Interference drag happens where the airflow around different parts of the airplane interact and create extra turbulence or resistance.
All right.
A common example is where the wing joins the fuselage. The way the air flows over the wing can interfere with the way it flows around the fuselage and create more drag than the sum of the drag from each part individually.
Okay.
And so fairings.
What are fairings?
Fairings are those smooth, curved pieces you see at these intersections, are designed to help the airflow blend more smoothly and reduce that interference drag.
And the last type of parasite drag is skin friction drag.
Yeah.
That sounds like it has to do with the surface of the airplane itself.
Exactly. Skin friction drag is the resistance created by the air molecules that are in direct contact with the aircraft's surfaces. Even a surface that appears smooth has microscopic roughness. The air right next to the surface kind of sticks to it. And then layers of air above it move progressively faster. This creates a boundary layer of slower moving air near the surface. A smooth, clean surface minimizes that friction.
So things like smooth paint.
Yeah. Smooth paint, flush rivets, keeping the airplane clean, all help to reduce skin friction drag.
Okay, so parasite drag is all about resisting our movement.
Yeah.
It's not directly involved in creating lift.
Yeah.
Now, what about induced drag?
Right.
You said that's the other main type.
Yeah. Induced drag is fundamentally linked to the fact that the wing is producing lift. It's an unavoidable consequence of generating that upward force. So to create lift, the pressure on the lower surface of the wing has to be higher than the pressure on the upper surface at the wingtips. This pressure difference causes air to want to flow from that high pressure area below to the low pressure area above, creating those swirling masses of air called wingtip vortices.
I've heard about those.
Yep.
So these are what cause induced drag.
These are what cause induced drag. Yeah. The energy that goes into creating those vortices and the associated downward deflection of the air behind the wing, which is called downwash, effectively tilts the lift force slightly backwards. This rearward component of the lift is what we experience as induced drag.
So you're not getting all of your lift purely upwards?
No, you're not.
Some of it is.
Some of it's being directed slightly to the rear. Which creates drag.
Okay, so if I need to generate more lift, does that mean I'll create more induced drag?
Generally, yes. Induced drag increases with the angle of attack. So when you need more lift, especially at lower airspeeds, you have to fly at a higher angle of attack, which strengthens those wingtip vortices and increases induced drag. However, induced drag is inversely proportional to the square of the airspeed. So as your speed increases, induced drag decreases significantly.
That's fascinating.
It is.
So parasite drag gets worse at higher speeds, and induced drag gets worse at lower speeds.
That's right.
It sounds like there's some optimal speed.
You've hit on a key point. Total drag is the sum of parasite drag and induced drag because one type increases with speed and the other decreases with speed. There's a specific airspeed where the total drag is at its minimum. This is a really important speed for pilots because it relates to the aircraft's most efficient gliding range
Okay.
and its overall performance.
We've covered a lot of ground with these forces.
Yeah.
Let's touch briefly on weight and balance. I know it's a detailed subject.
Yeah.
But how does it relate to what we've been discussing?
So weight, as we established, acts downwards through the center of gravity.
Right.
Lift acts upwards, effectively centered around the wing's center of pressure.
Okay.
The position of the center of gravity is crucial for the airplane's stability.
Okay.
Aircraft are designed with the aft limit of the CG ahead of the center of pressure for most flight conditions.
Right.
And this helps the aircraft naturally want to return to a stable pitch attitude.
Okay.
In stable level flight, the total weight must be exactly balanced by the total lift. If lift exceeds weight, you'll climb. If weight exceeds lift, you'll descend.
Makes sense.
Yeah.
Now, something that's definitely on the minds of new pilots is wake turbulence.
The wake turbulence.
How does that connect to the aerodynamic principles we've been talking about?
So wake turbulence is a direct result of those wingtip vortices that we discussed with induced drag. So those vortices create a turbulent wake behind the airplane.
Okay.
And this wake can be very dangerous for following aircraft, especially smaller ones.
Right.
The vortices are strongest when the generating aircraft is heavy. It's flying clean.
What does clean mean?
So clean means with the flaps and gear up and at a slow speed, because this requires a high angle of attack to produce the necessary lift.
Right.
These conditions often occur during takeoff and landing.
So what are some of the key precautions I should take to avoid wake turbulence?
Several important things to keep in mind.
Okay.
You always want to try to stay upwind.
Okay.
And avoid flying through the flight path of a larger aircraft.
Right.
When taking off behind a heavy aircraft,
yeah.
Make sure you rotate for takeoff beyond their rotation point.
Okay.
When landing behind one. Try to approach slightly above their flight path and aim to touch down beyond their touchdown point.
Okay.
Also avoid following another aircraft on the same route at the same altitude, especially within 1,000 feet vertically.
Got it.
Helicopters also produce significant wake turbulence from their rotor downwash and forward flight vortices.
Interesting.
Wind can also cause these vortices to drift.
Okay.
So always be mindful of the wind conditions.
Okay.
And if you're ever unsure about the path or dissipation of wake turbulence, a general rule of thumb is to wait at least 3 minutes before proceeding.
Got it.
Yeah.
Another interesting concept I've come across is ground effect.
Ground effect.
What is that?
It's a phenomenon you'll notice when you're flying very close to the ground, typically within about 1 wingspan's height.
Okay.
The proximity of the ground alters the airflow pattern around the wing. It restricts the downward movement of air behind the wing, which in turn weakens those wingtip vortices we've been talking about.
And how does weakening those vortices affect the forces on the airplane?
So because the wingtip vortices are weaker, the induced drag is reduced. In fact, at a constant angle of attack, you might even see a slight increase in the lift coefficient. This reduction in induced drag can create a sensation of floating during landing, where the airplane seems reluctant to settle onto the runway.
Yeah, I've heard about that.
Excess speed during the landing flare can exaggerate this effect. Conversely, during takeoff, as you climb out of ground effect, you'll experience an increase in induced drag. And you might need to increase your angle of attack or add power to maintain your climb.
Got it.
You might also notice a slight decrease in longitudinal stability.
Sometimes associated with a tendency for the nose to pitch up.
Okay.
Yeah.
Finally, let's just briefly touch on the axis of an airplane and stability.
Sure.
I know these are big topics on their own.
Yeah.
But how do they relate to the forces we've been discussing today?
So understanding the 3 axes of an airplane. The longitudinal axis for roll. The lateral axis for pitch and the vertical axis for yaw is fundamental to understanding how you control the aircraft using the flight controls and how it responds to those inputs and external disturbances. Stability refers to the airplane's inherent tendency to return to a state of equilibrium after being disturbed. We talk about static stability, which is the initial tendency to return, and dynamic stability, which is how it behaves over time after that initial reaction, longitudinal stability.
Stability in pitch is greatly affected by the position of the wing and horizontal tail relative to the center of gravity. The downwash from the wings affecting the tail also plays a critical role in providing a restoring force. If the nose pitches up or down, even the thrust line of the engine can have an influence on stability.
So as you can see, there's a really fascinating and interconnected set of forces and aerodynamic principles that make flight possible.
Absolutely.
Understanding these basics, lift, drag, thrust, weight, and how angle of attack ties it all together is absolutely crucial.
It is.
As you move forward in your pilot training,
it is.
Pay close attention to how these concepts are demonstrated and applied during your flight lessons. And don't hesitate to ask your instructor to explain them further.
Absolutely.
This is just the beginning of a very rewarding journey into the world of aviation.
Absolutely.
Thanks for listening.